They did inform me yesterday afternoon that they will have room 165 on campus open and logged in for us. So any of you that are having issues or any troubles trying to log in from home or find a place to log into class on Thursdays, that room will be available to us to use for this course, so that we have that. Okay, so yesterday we left off, we talked about all these different operations and how the count and the name come in with the place value on defining on how those operations have to be done with larger numbers. Does anybody have any questions off the homework from yesterday?
Just, I did most of them, and do you want pictures of it?
No, I don't collect the homework. I trust that you do it. Is when I give you work time at class, as long as you're here working, you get credit for the homework and participation. I have about 100 and I think I counted 113 students here. I can't shuffle the homework back and forth every day. It'd be a horrible email nightmare. So yeah, I just trust
Right.
that you did. I don't
So,
collect the homework.
okay. So it's more or less practice
Yeah,
for the
basically,
quizzes and
exactly. The homework
okay,
is to
great.
prepare you for the
That's
quizzes and tests. And to be honest,
great.
like I said
Thank you.
yesterday, some of the problems at the beginning of those assignments are pretty simple. I have no problem if it's something you've seen before and you're fairly good at. If you want to skip those simple problems at the beginning and just do the more difficult problems at the end, I don't have a problem with that as long as you're feeling like you're prepared for the quizzes or tests. Now, some problems that usually come up as questions off of these assignments, I'll do a couple of them here. One looks something like this. This is an electrical circuit. And in a circuit, we have resistors. Resistors are anything that resist the flow of current through that circuit. Could be a light bulb, it could be an electric motor, could just be an actual manufactured resistor designed to slow down the current. Or should I say resist the current? Oh, sorry, I wasn't yawning in my last class. I don't know what's going on today. So the symbol for resistance is called the ohm, and it looks like an upside down horseshoe like that. It's actually the Greek letter omega. And so let's label these 40 ohms, 20 ohms, 30 ohms here, and 50 ohms. This is what is referred to as a series circuit. What the word series means there is one after the other. So if you trace the flow through this circuit, you'll notice the current goes through one resistor after the other. In a series circuit, the total resistance is just the sum of the resistances. In other words, just add them up. So the total resistance here is just 40 plus 20, 30 plus 50, which is a total of 140 ohms. Another one that comes up that's very important in construction fields and in welding, manufacturing, something that looks like this. This type of thing comes up on a blueprint a lot. And reading blueprints, even if it's just looking at your designing your own home or anything like that, it's an important skill. And when we look at this, in most blueprints, things stay pretty square like this. Pretend those are square corners. The dimensions that can be used together are only the dimensions that go in the same direction or in the same orientation. So this dimension here is vertical. It can only be combined with this dimension and this dimension. Those are all the vertical dimensions. This one here is horizontal. It can only be combined with those other horizontal dimensions. And these dimensions can be combined with either addition or subtraction, depending on how they're laid out. Let's say this here is 42 millimeters, and this piece over here is, let's go 31 millimeters. What can I find from that? Well, the only other blue dimension, only other vertical dimension is this one here. And these two are the shorter ones, have to add up to the longer one here. So to find that short piece, I'm just going to do the 42 minus 31, giving us 11 millimeters. If we look at the other dimensions, maybe I have 44 millimeters here and let's go 26 millimeters here. If I want to find this dimension, that's the longer dimension. It's going to be the sum of the smaller ones. So I'm going to add these two together. 44 plus 26 gives us 70 millimeters for that dimension. Now here I color coded them and I only put the dimensions out there a little bit at a time. It can be a little trickier when you have all the dimensions labeled looking for specific missing dimensions. We might have, let's say this is 18 millimeters, 8 millimeters. And we'll call this here 26. And up here we'll call this 40. And let's say I am looking for dimensions A and B. To find dimension A, it's a vertical dimension. So the only other dimensions that go in the same direction or same orientation of that are the 8 and the 18. Now I do have to check, I should have pointed this out in the previous problem, I do have to check that they represent the same length. And dimension A goes from here up to here. The combination of the 8 and the 18 also go from here up to here, and there's no gap. This piece here connects the two of them. The fact that this is horizontal at a right angle, at a square corner to those other two dimensions, tells us that there is no difference, there's no gap between those two ends of those dimensions, by the way. So then to find dimension A, we just add those smaller pieces together. 18 millimeters plus 8 millimeters gives dimension A is 26 millimeters. Going the other direction, trying to find dimension B here, well, it's horizontal. We have to use the other horizontal dimensions. Again, this 40 millimeters goes from here all the way to here. We have to check, make sure the combination of the other two dimensions does it as well. Well, B starts here and goes to here. The 26 starts at the same spot B leaves off and goes to that other end. So they do cover the same distance. So B plus 26 has to be equivalent to 40. So to find B, it's going to be 40 millimeters minus the 26, giving us 14 millimeters for B. That may seem like a very simple problem, but every year I find that students struggle more and more with that, figuring out what dimensions have to match up to be combined on a simple drawing or blueprint like that. Okay, on with our new material for today. Today, we're going to talk about integers. I always joke that integers are, and for many people, the only integers they'll ever encounter is in their checkbook. What an integer is it's all the whole numbers that we have talked about so far, and they're negatives. So like I said, I joke about the checkbook, but integers actually do pop up quite a bit. In bookkeeping, you have losses. Those would be negative numbers. In engineering and design, you have deflections that are negative. You have positive bends, negative bends, and things like that. So it does come up more than you would think. To work with these integers, the negative numbers, we have to review. Remember, yesterday we talked a little bit about combining counts. And we said really the only combination of counts is addition. We looked at something like 5 plus 3. And we said the way it works on the number line, those numbers are represented by what we called vectors. Remember, vector is kind of a fancy word for a simple concept. The 5 is just an arrow that starts at 0 and goes to 5. That's our vector for 5. The 3 is just an arrow that starts at 0 and goes to 3. That's our vector for 3. To add 5 and 3, we just physically combine the vectors. That vector for 3, we put it there. And of course, that goes up to 8. That goes up to 8, so 5 plus 3 is 8. Now, we all knew how to do 5 plus 3. We knew that was 8. But let's take a look at what happens when we put a negative in there. Let's do something like 7 plus a negative 4. Now, your textbook generally will put parentheses around. If the negative is the second number, it'll put parentheses around it, just so you don't confuse that negative sign in front of it with a subtraction operation. It does that just to make sure you know that is a negative number. So if I draw out these vectors, 7, of course, starts at 0, goes to 7 like that. 4, or negative 4, I should say, starts at 0 and goes to negative 4. When I go to combine those, negative 4 so I can move it. I can move either one, actually. If I move the negative 4 and combine it with the 7, probably a little bit off there. You can see I end up at the 3, excuse me. There we go. I end up at 3. Or I could have done the other way. I could have moved the 7 if I wanted to. Makes no difference. Put that 7 on the negative 4. You see, I still end up at 3 either way. For that reason, addition is what we call commutative. That just means it does not matter which vector we move. It doesn't matter which number we put first. Here we could have started with the 7 and combined the negative 4, which is what we did here. We went 7 and then back 4, the negative 4. Or we could have started with the negative 4, which is what we did here, and then put the 7 with it. Either way, we end up at 3 on the number line. That answer is 3. Now, I don't expect that you're going to draw out vectors every time you have to add integers, anytime you have to add negatives. But it does help. I keep that picture in the back of my mind when I am working with negative numbers. If I have something like a negative 29 plus 43, in the back of my mind, I have this picture. There's 0. Negative 29 goes this way. Positive 43 goes the opposite direction, so I'm going this way. 43 is bigger than 29, so it goes past 0. So this picture tells me two things. One, it tells me my answer is positive because I end up on the positive side of 0. The other thing it tells me is that since these vectors or arrows point in opposite directions, the answer, the result, is the difference in the length of those arrows. So the big arrow is 43 units, the small arrow is 29, the difference is 14. Now you heard me use that term, the length, put my T in there, length of the vectors. The length of the vectors is what's referred to as the absolute value. And that's all it's referring to is the length of that vector. The symbol for absolute value looks like this. Just a bar on each side of the number. So that's saying the absolute value of 29, well, that's just 29. Its length is 29. The absolute value of 43, well, that's just 43. Its length is 43 units long. So when we're dealing with integers, a lot of what we're doing, when I say the size of the integer, what I'm really talking about is that absolute value, the length of that arrow or vector in my little chart here. Because technically, a positive number is always larger than a negative number, but I'm referring to the length of that vector, that absolute value. Let's do another example. We might have 51 plus a negative 74. So now here again, I'm picturing there's my 0. From that 0, we go 51. Well, that's this direction, 51 units. We have the negative 74. Well, two parts to that. It's negative, so it goes the opposite direction. It's going to go this way. 74 is a larger absolute value than 51, so this goes longer than the 51. It goes past the 0. So this tells me my result is on the negative side of 0. So my answer is negative. Once again, those vectors point in opposite directions. So the size of my answer, the absolute value of my answer, is the difference in those sizes, the difference in those absolute values. So the longer vector was 74, minus the smaller one, which was 51, which is 23. So that result is a negative 23. We might have something like this. Negative 32 plus negative 27. So when we look at this picture, here we start at 0. Negative 32 goes this way. Negative 27 goes the same direction. It keeps going. So this picture, again, tells me two things. Well, they both go in the negative direction, so I'm definitely ending up on the negative side of 0, so my answer is negative. Since the vectors point in the same direction, the absolute values, the size of my result, is just the combination of the two absolute values combined. So come on now. The first one, the negative 32, that's 32 units long. The negative 27 is 27 units long. I add those to get 59 units. So my answer is a negative 59. Like I said, I don't expect you to draw out a number line, but I often will do this little sketch when I'm working with these negatives in order to make sure I keep track of what I'm supposed to be doing with them. Well, where things kind of get turned upside down is with subtraction. So to talk about subtraction, let's start out with at least a problem that we know with positive numbers. Let's start out with something like 8 minus 3. 8, if I asked you to draw out the number line for this, most of you draw out the same picture. You'd have 8 minus 3 is 5. We all know that 8 minus 3 is 5. We've done that since about, well, kindergarten, actually, to be honest. So we know that result. But if we look at this picture here that I just drew, the vectors, that picture looks an awful lot like 8 plus a negative 3. The reason being is because that's exactly what it is 8 plus a negative 3. We mentioned back on the first day that subtraction wasn't really its own operation. It's the reverse of addition. And in truth, if you get into the really formal algebra, subtraction doesn't exist. It's a shortcut. The operation of subtraction, that symbol that we mean it uses the subtraction symbol, technically means add the opposite. Well, first of all, what's the opposite? An opposite of a positive number is a negative number. The opposite of a negative number is a positive number. It's the opposite sign. The second is the opposite of what? Well, an operation always operates on the number that comes after it. So what's being subtracted here is the 3. So subtracting 3 is equivalent to adding the opposite of 3. What does that mean? Adding the opposite of 3? Well, that's just a fancy way of saying adding negative 3. So subtraction literally is a offshoot of addition. It's a shortcut for adding negative numbers. Now, if I have something like 47 minus 16, I do not expect you to turn that into 47 plus a negative 16. To me, that just made the problem more difficult. We've all done subtraction with positive numbers. 47 minus 16 is 31. We can do that. We know how to do that. So I don't expect you to change that. But if either of those numbers in the subtraction is negative, it's often easier to change it to addition. It's easier to understand. For example, I might have a negative 35 minus 17. That can be very confusing to have subtraction with one of the numbers being negative. But if I change this, remember the subtraction operates on the number coming after it. So it operates on the 17. So the negative 35 does not change. Subtracting 17 is equivalent to adding the opposite of 17. The opposite of 17 is a negative 17. So this problem is equivalent to negative 35 plus a negative 17. Now I can use my vectors. Now that it's addition, I can use the arrows. So from 0, I have negative 35. Negative 17 goes the same direction. That tells me that my answer is negative. And since the vectors go the same direction, I add their absolute values to get 52. The negative 52. The one that always confuses people is this one. 24 minus a negative 53. When I look at this one, remember that subtraction operates on what comes after it. We are subtracting the negative 53. So the 24 here is not affected when we make our change. Subtracting a negative 53 is the same as adding the opposite of negative 53. So we're adding the opposite of a negative 53 is a positive 53. So this is simply an addition, a positive number addition here. 24 plus 53, you all know that's 77. So we don't even need the vectors for that one once we change it to addition. Similar to that one, oh, my scroll isn't working real well today. We have something like this. A negative 62 minus a negative 74. If I tried to do this one as a subtraction problem, it would have my brain going in circles. It's just not a simple problem. But again, we can change it to addition. Remember the subtraction Excuse me, I haven't got my teacher voice for the semester yet. The subtraction operates on the number that comes after it. So the negative 62 is unchanged. Subtracting a negative 74 is the same as adding the opposite of negative 74. So the opposite of negative 74 is a positive 74. So this is negative 62 plus 74. Now that it's addition, I can use my vectors. So negative 62 goes this way. 74 is positive, goes the other direction, and it has a bigger absolute value, so it's longer, so it goes past 0. Telling us that our answer is on the positive side. Since those are opposite directions, it's the difference of their absolute value. So 74 minus 62 is 12. That's a positive 12, is that result. So again, changing subtraction into addition allows us to use these vectors. Now, if I just have a problem like 42 minus 18, I'm not going to bother to change that because, like I said, I know how to subtract 42 minus 18. I know how to do that. I don't need to change it into addition. It's a positive problem. It's something I know how to do. But whenever you get the negatives, the integers start appearing in there, often changing it to addition is the only way to make it make sense. For multiplication, we had mentioned yesterday that multiplication is really repeated addition. So 5 times 3 is 3 5s added together. 5 plus 5 plus 5 is 15. On the number line, that simply meant we had that vector appear 3 times, taking us to 15. So you can see the only way of combining counts is really addition. What if we throw negatives in there? Well, if I make this a negative 5 times 3, that using that same strategy to break it down is relatively simple. That's negative 5 plus negative 5 plus negative 5. We could add those to get negative 15. If you wanted to use the vectors, we'd be using the vector for negative 5, which just goes the opposite direction. And you can see 3 of them end up at negative 15. It's a little trickier, however. In fact, I don't need the multiplication symbol in here if I use the parentheses. That parentheses, whenever there's a number outside of parentheses with no symbol like that, it means multiplication. A little trickier to envision 5 times negative 3. Up here, 5 times 3 was saying take the 5 and add 3 of them together. Negative 5 times 3 was saying take the negative 5 and add 3 of those together. Well, this is trying to say take 5 and add negative 3 of them together. Well, you can't add something a negative number of times. So for this one to make sense, just like addition was commutative, we said it didn't matter which one we started with. Multiplication is also commutative. I can switch the orders. Now notice I did not say anything about subtraction or division. Those are not true. You cannot switch the order of numbers in those operations. Only works with addition and multiplication. But 5 times negative 3 can be changed to be negative 3 times 5. And now that it's in that form, that's saying take negative 3 and add it together 5 times. That I can do. Negative 3 plus negative 3 plus negative 3, negative 3 plus negative 3. And we can see that gives us, again, negative 15. And if you wanted to do the vectors, negative 3, negative 3, negative 3, negative 3, negative 3, where we're at. The tricky one to at least conceptualize is what if both of them are negative? Negative 5 times negative 3. Well, I cannot take a -5 and add it together -3 times. I can't add -3 of them together. Even if I switch the order and do -3 times -5, it doesn't help. I can't take -3 and add it together -5 times. It doesn't work. So the way this is written, it really doesn't make sense. According to the definition of multiplication, this can't be done. Well, we have all been told the answer to this is a positive 15. That you multiply two negatives, you get a positive. That's just what we've been told. That's the rule. Well, the question we want to ask in here is why? According to the definition of multiplication, like we said, neither of those problems can be done. You can't add something a negative number of times. And this actually happens a lot in math, where we run into something that our basic definition breaks down and it doesn't work. So in order to make sure that we can do it, we look for a pattern. What do I mean by look for a pattern? Well, let's do this. Let's start out with -5 times 3. We all know that's -15. We just saw that. Well, to establish a pattern, I keep all of the problem the same and I only change one thing to see how it changes the result. So in this problem up here, I'm going to keep everything the same except for the 3. And of course, the result will change as a result of changing the 3. So the -5 is the same. We're still multiplying, but I'm going to change that to a 2. -5 times 2 is a -10. Now I see what happened here. When I reduced this by 1, my result here actually went up by 5. Let's keep going and see if that pattern continues. So again, I keep the -5. I change this number. I reduce it by 1. So it goes from 2 down to 1. -5 times 1 is a -5. And yes, my pattern continued. Once again, I reduced this by 1. My result over here increased by 5. If I continue reducing that by 1 from 1 down to 0, -5 times 0 is 0. That pattern held true. I reduced this by 1. My result increased by 5. So if I go the next step, I reduce this by 1 again. 0 minus 1 is a -1. This has to be increased by 5. 0 plus 5 is 5. If I continue that, -5 times -2, again, I reduce this by 1. I have to increase my answer by 5 to get 10. -5 times -3, well, I increase by 5 again to get 15. So when your teachers told you that when you multiply two negatives, you get a positive, the only reason that is true is because it continues or it fits this pattern. So we have defined that to be true, that when you multiply two negatives, you get a positive, so that we can keep consistency in our patterns in math. Like I said, that happens with exponents and a lot of other things in math as well, that the definition doesn't work, so we look for a pattern. So the net result here is if I am multiplying and I have a positive number times a negative number, positive times a negative gives us a negative, and then I just multiply the absolute values. 8 times 3 is 24. Or if I have a negative times a positive. Positive or negative times a positive is a negative result. And we multiply the absolute values. 6 times 7 is 42. So here you can see anytime I'm multiplying and one number is positive and the other one is negative, it doesn't matter which is which, the result is a negative result. Of course, if both of the numbers are positive, there's no question that answer is going to be positive as always. And what we just saw in the pattern here, if both numbers are negative times a negative makes a positive. Multiply the absolute values. 3 times 11 is 33. Positive 33. So if there's two different signs, the result's negative. If they're both the same sign, whether they're both positive or both negative, the result comes out to be positive. Now, when we divide, we've been taught that same pattern. Two positives and two negatives combine to be positive, or one of each combines to be negative. The question is why? Well, yesterday we looked at one definition of division as being repeated subtraction. Another definition of division, as we mentioned on the first day, is the reverse of multiplication. What does that mean? Well, that means that when I am doing something like 12 divided by 2 equals blank, that is actually asking us to complete a related multiplication problem. That related multiplication problem looks like this. It actually just kind of going backwards. Blank times 2 equals 12. Whatever fills in this blank to make that problem true also fills in that blank to make the division problem true. Well, we know that 6 times 2 makes 12. So 12 divided by 2 makes 6. Now again, we all knew 12 divided by 2 was 6. We didn't need that related multiplication problem. But we can use it now to work with the integers. If this is a negative 28 divided by 7, well, that's saying what times 7 equals negative 28. Now, let's break this down here. We just discussed that in order for the result of a multiplication problem to be negative, we have to multiply one positive and one negative. Well, the 7 here is positive. That tells us that whatever this is has to be negative. Well, it's 4 times 7 is 28, so it's a negative 4 times 7 makes a negative 28. So negative 28 divided by 7 is a negative 4. If I have a negative 32 divided by negative 4, well, that's asking us what number times negative 4 equals negative 32. Well, again, we just discussed in our multiplication, the only way that the result of a multiplication problem can be negative is if I'm multiplying one positive and one negative. Well, the negative 4 here, that's already negative, so this one has to be positive. It would be a positive 8 times negative 4 makes negative 32. So this has to be a positive 8. Or we might have, let's do 24 divided by a negative 8. Again, that's asking us what times negative 8 equals a positive 24. Well, again, up above, we saw that the only way two numbers can multiply to make a positive is if they're either both positive or both negative. Well, the 8 here is already negative, so that means the other number also has to be negative to get a positive result. Let's say negative 3 times negative 8 makes 24. So this here has to be a negative 3. 24 divided by negative 8 is a negative 3. Well, you can see here that this follows the same pattern as up above. If both numbers were negative, we get a positive result. If there's one of each, one positive and one negative, the result is a negative. So the same pattern as with multiplication. This same type of logic, by the way, can be used to define the result of that subtraction problem. 5 minus 2 equals blank has a related addition problem. Blank plus 2 equals 5. So rather than changing it to adding the opposite, we could change it to that related addition problem. I think it's just simpler to do adding the opposite myself. Okay, I promised to give you guys a little bit of work time, so I'm going to do that today. Out of your book, there's going to be a few pages here. On page 111, 1 through 39, the odd-numbered problems. On page 114, have you look at 1 through 35, the odd-numbered problems. And on page 116, and we'll break it up a little bit, 1 through 39, the odds. And then I'm also going to have you do some word problems here, 51 through 79, the odds. Now, as I said yesterday, the first few problems are very easy. Feel free to skip ahead, go deeper into the page to the more difficult problems. Just make sure you're doing a handful of those more difficult problems at the end. So as we mentioned earlier, that you are ready to do the quizzes or tests. Also remember, you do have that solutions packet on Blackboard. So that you can look over that and you can check your answers with that solutions packet. And you'll know if you're doing them right. I don't want you to do a bunch of problems wrong and then have bad habits you have to break up later. So I'll give you the last 5.5 minutes here to get started on your homework. We do have, remember, give you a little bit of a heads up here. On Tuesday will be our first quiz. So if you've had any problems accessing Blackboard, make sure you send an email to My Help. That's their help desk. myhelp@witc.edu. Because Blackboard is going to be the mechanism that I use to give those quizzes to you. I will show you on Monday how those are going to be accessed. Rather than returning them through email, I'll have you upload them in a Dropbox in Blackboard. That way I don't have to keep track of who's in what class. It'll make it a little easier for us, and you won't have to remember to be so picky about your subject line in your emails. Okay, I will shut up. I'll shut off the recording here and let you guys work. If you have any questions, just give me a yell. I'll be here.